Early computer science was built on absolute certainty. Human programmers wrote explicit, deterministic rules, and the machine executed those exact commands. If X happens, do Y. But the real world is messy. As the problems we asked computers to solve grew increasingly complex, it became impossible for humans to anticipate and code every single rule or edge case. To handle that complexity, the industry pivoted heavily toward machine learning and neural networks. As this excerpt outlines, the neural network approach created a black box crisis. These models require massive computational power and energy to train. Worse, their internal logic is largely unreadable to humans. In high-stakes environments like medicine or autonomous driving, a neural network might make a fatal error, and we have no way of tracing exactly why it made that decision. Decades ago, a Soviet mathematician named Michael Tsetlin developed a stochastic learning algorithm that operated on simple rules and probabilities. Recently, researchers used his work to build a completely different AI architecture, the Tsetlin Machine. Instead of complex calculus, it is built entirely on simple Boolean logic. To build computing systems that are both highly capable and actually safe to deploy, we need an intelligence that can learn from complex data while remaining readable at its core by the people operating it. The foundation of its Tsetlin machine is a concept called Boolean features. This means the machine translates all incoming observations into strict binary states, true or false. If the machine looks at a vehicle, it breaks it down into distinct properties. Does it have 4 wheels? True. Does it have wings? False. It records both the presence of a feature and its negation. Knowing a car lacks wings is just as identifying as knowing it has wheels. This graphic shows how the machine stores these literals. Instead of statically remembering a rule forever, it places each feature on a graded memory scale, ranging from 1, or maximally forgotten, up to 10, meaning maximally memorized. By treating physical traits as binary literals and placing them on a fluid axis, the machine establishes a mathematical canvas where learning occurs dynamically. Learning happens through 3 specific feedback loops. The first is recognize feedback. When the machine consistently sees a feature that accurately identifies an object, it pushes that literal higher up the memory scale. The second loop is erase feedback. Random noise, coincidences, or irrelevant data points are actively suppressed, sliding down the scale until they fall out of the machine's working memory entirely. This data table illustrates the third mechanism, reject feedback. This actively memorizes negative features that uniquely distinguish one class of object from another. It forces the system to remember what an object is definitively not. These 3 competing feedback loops allow rigid if-then rules to organically adapt, eventually stabilizing on the specific patterns required to classify objects correctly. This diagram of a Markov chain shows that the system doesn't rely on one giant algorithm. A Tsetlin machine generates a massive number of independent rules, each stochastically testing different probabilities and pattern combinations simultaneously. As illustrated by this scale, the machine makes its final decision through a majority vote. Each independent rule evaluates the data and casts a mathematical vote for a specific classification. The heaviest side wins. To keep all the rules from just voting on the exact same obvious features, the system uses a vote margin. This forces the machine to seek out a specific buffer of extra votes, effectively pushing redundant rules to go find entirely different complementary patterns in the data to secure the victory. These independent logic gates never communicate with each other, yet through their individual voting mechanisms, highly coordinated and complex problem-solving emerges. Looking at these printed equations, the contrast with modern black box AI becomes obvious. The final complex output of a Tsetlin machine is completely transparent. It is written in plain text, human-readable if-then logic. This architecture translates directly into hardware efficiency. Neural networks process floating-point math, which requires specialized, power-hungry chips. Tsetlin machines operate purely on true-false Boolean algebra. This allows for hardware-near bitwise operations. It means computing at the deepest, simplest level of a computer processor. The result is a drastically reduced energy footprint and incredibly fast processing speeds, making it ideal for edge computing and small smart devices. Mainstream AI development often assumes that higher accuracy requires higher opacity. The Tsetlin machine challenges this by achieving learning results through logic that stays visible to the human eye. It is no longer enough for artificial intelligence to merely output the correct answer. To deploy these systems safely, they must be capable of showing us the exact logic they use to arrive there.